Hello everyone, my name is Gabe and welcome to another video. In this video I wanted to record my master's thesis oral defense. Just to have a record of it, I will most likely put it on my YouTube channel, which is who I'm talking to now. So hello. My thesis is entitled Searching for Anderson Localization of Ultrasound in Dielectric Mesoglasses. Okay. Now, a brief outline for the talk here. I'll begin by introducing Anderson localization in its earlier stages and how it's relevant to ultrasound. I will then talk about the actual mesoglass samples, how we make them, some information about the motors and assembly, which are important to the experiments, and then I will discuss the experimental methods themselves, and then the results. Then I will conclude and summarize. And so, the widely cited paper written by Phil W. Anderson more than 60 years ago talks about the effect which disorder in material has on the diffusion of energy within them. On the atomic scale, on the left, in an ordered periodic lattice, the overlap of neighboring electrons' wave functions result in energy bands, which make way for standard diffusion or high conductivity. In the disordered lattice case, Anderson argued that at a certain degree of disorder in the potentials of electrons from one site to another, electrons can become frozen in position, not in individual atoms, but over length scales larger than the interatomic spacing. In essence, halting transport of energy completely, or turning a conductor into an insulator. That's why it's so interesting. So then, by the 1980s, the study of wave localization was extended to classical waves in light or sound. In 2008, Anderson localization of ultrasound was successfully observed in an aluminum mesoglass by researchers from U of M, where they showed ultrasound can be localized in mesoglasses, which is again just a mesoscopic analog of atoms using spherical beads instead of atoms. And so now the question is, can we see Anderson localization in dielectric material? This motivation comes, of course, from L.S. Levetov, a Russian physicist, who predicted the absence of localization of vibrational modes due to dipole-dipole interactions. As we know, ultrasonic excitation induce electric dipole moments, and these electric displacements may couple long range. This communication between induced electric dipoles at R1 and R2, for example, no matter how weak, is enough to inhibit localization in dielectrics. An extreme example of how dipoles can be excited by sound is shown for piezoelectric material, as you can see in the top right, but the effect is much more weak and subtle in dielectric materials. And so yes, Levetov said that no matter how weak it is, it's enough to destroy the localization of energy. And so generally speaking, the propagation of an ultrasonic wave in a disordered medium can be thought of as a random walk. Right. And so in the common case where we have weak disorder, we have negligible interferences. The wavelength of the wave is much smaller than the scattering mean free path L. Here, multiply scattered waves propagate diffusely. However, in the localized regime, we have a lot more disorder or heightened disorder. And so these recurrent paths, whereby waves go on loops and come back in phase, are more probable. This goes hand in hand with KL around the order of 1, where K is the wave number equals to 2 pi over lambda. And in this regime, the multiply scattered waves become trapped. The model that we use here is a diffusion approximation in the diffusive case on the left, where we can see the energy intensity W and the diffusion coefficient dB, or the Boltzmann diffusion coefficient, where that's just a third of the product between or of the energy velocity VE and the transport mean free path L star. And so now, as the disorder goes up, scattering will go up, interferences go up, and so we can't use a diffusion approximation anymore to describe the wave behavior in this type of regime where we have a lot more disorder and scattering. And so this leads to a renormalization of D in order to accurately or more accurately describe it. And the self-consistent theory, or SCT, does exactly that. Excuse me. Whereby you can see an inverse relation between the probability of a wave returning to its position, here C of R omega, and then this localization length psi is what we use as an important parameter, and it is the average decay of intensity at a position. And so a few samples were made and were discussed in this presentation, 2 of which I made. They are, and then another one was made by a previous researcher. The importance here is that they have various thicknesses, but the process by which we make them is the same. The samples are comprised of disordered networks of these borosilicate beads, 4 millimeters in diameter. I'll draw your attention to the softening temperature, which is an important parameter, which makes it accessible for us, which means we can actually make them in the lab. We don't have to seek out any high-end equipment. And the process is as follows. We use a cavity-populated mold that ensures the random disorder, the random arrangement of the beads in the sample, and then once the sample is well organized and densely packed as much as possible, we put it into the furnace, where we use a specific intricate heating configuration to reach the softening temperature just long enough so that we don't over or under sinter the sample. And then once the sample is done, we put it into a vacuum housing, we mount it onto a steel rod, and we lower it into the tank. And then here behind my picture, you can't see, but it says that the optimal sample will be able to withstand the handling that's required to put it in, or to put it in a vacuum housing, mount it onto a steel frame, or a plastic frame, and then the rod, and then, there's a lot of handling that comes into it. So the optimal sample is one that can withstand the handling while still having weak bonds between the beads in order to retain the spherical or sphericity of the overall beads inside of the sample, which we reached. And so here I wanted to include this slide to talk about the motor assembly. Using these motors, we're able to move the generation, detection, and the sample simultaneously in order to access many realizations of a disorder in the sample instead of scanning at one position. So, and then in addition, since we're only interested in the sound or the signal that interacts with the bead network, we must maintain a sufficiently low pressure inside of the vacuum housing during the entirety of the experiments. And here's a schematic of the vacuum system. And so the initial experiment that was done outside of the water tank is to measure the resonant frequencies of one bead and multiples of beads, or mini samples. And so here, as you can see, we inside of a vacuum chamber, we put the one bead or the mini sample sandwiched between in between the emission and the detection. We send a Gauss 2 input pulse. We take the raw signal, and then we take the FFT. We use a windowing, a Blackman-Harris windowing to narrow, or to get a better resolution of some peaks, not all, but it does help. And so as you can see here on the right side, we get a pretty good agreement, or a correspondence, between the experimentally measured peaks and the COMSOL simulated peaks. And this allowed us to take these COMSOL peaks and visualize them. As you can see in this slide here, each peak corresponds to a vibrational mode of each bead, or of one bead, I'm sorry. And this allows us to see what exactly is happening at each of these ultrasonic excitation frequencies. A few of these modes have a degeneracy of up to 6 or 7, which is why you might get some spectral leakage in certain instances. And yeah, so our good agreement between the experimentally measured and the COMSOL simulator frequencies allowed us to visualize this with good confidence. And so we continue to so these are the resonant frequencies of the mini samples. There's 1, 2, 5, 10, and 20. And here we notice that there is a shift. So as the number of beads go up in the system, we get a shift in resonant frequencies to the right, as well as a broadening or a spectral leakage to the right as well. And then as you add more and more of these beads into the sample into the system to get an actual mesoglass sample, what happens is we no longer have these sharp peaks, rather frequency bands. And this graph in the middle is the transmission coefficient of the complete samples, and as you can see, there are dips in frequencies. And in these dips is where there's less signal coming out. And so it is important to note that these are interesting frequency ranges where localization may be observed. And so the initial experiment that was done inside of the water tank was to measure the coherent pulse. This we measured to get information about we measure the phase velocity and the scattering mean free path, which then allows us to calculate or to characterize the scattering power of the sample KL. And so here for the two samples, we get a KL of around the order of 1, and then for the thickest sample we had, because it was so thick, we get attenuated and we didn't get as much signal on the other side, so we just took the average of the two because of the similarities in the way we fabricate the samples. This allowed us to make that approximation. But in essence, as you can see here on the right, the coherent pulse is the one that survives all averaging. So if you average all of this coda, all of the multicolored stuff, you will retain the coherent pulse that was initially sent in. And the next experiment that was done to actually investigate the lateral expansion of the intensity on the other side of the sample was the TC transverse confinement experiment. Here we measure the intensity not only as a function of time, but the position rho, the lateral position rho. So we measure the intensity at the on-axis position and at the off-axis, I of rho of t. And then, since each of these measurements individually are ridden with absorption, we track the ratio of them. In the diffusion approximation, this takes a Gaussian shape. But yes, if we take the ratio of the two, the absorption cancels because the measurements are at the same time t. And so we solve for the width squared, which is just the width squared, or the width of the expanding halo, or the diffuse halo, which you can't see behind my picture, but it just says we characterize the expansion of the diffusion using this width squared parameter. And width squared equals to 4 dt in the diffusion approximation, because the expansion of the halo is linear in time with, again, an effective diffusion coefficient d. And here on the bottom left is a picture of the experimental configuration inside of the water tank. Here are the results from the TC experiment. In the diffuse regime, we see a linear. In the top row, we see the times of flight. And then in the bottom row, we see the width squareds of the diffuse halo. Each column represents a different sample. And so we see a rapid decay in the times of flights, which corresponds to a linear increase in the width squareds. We were able to fit a line to the first three smallest values of rho, which what has been done in the literature in the past when studying Anderson localization of ultrasound in mesoglasses. However, we wanted to explore it a bit more, and so this is the linear, or this is where we still use the diffusion approximation. Excuse me. And so, as we scan the frequencies, we are approaching this subdiffuse regime. We're able to assess the intensity expansion here, where we're no longer linearly expanding in terms of the diffuse halo. We are a bit more localized, and so the expansion of the halo is slowing down in time, as you can see by the not so rapid decay of the TOFs, which correspond to a non-linear behavior in the width squareds. As we continue on to the near localized regime, we are even more localized, and so the width squares bend over even more, which means the diffuse halo is slowing down again, which is characterized by these L/X here at the top right of each subplot on the bottom row. And another thing that's important to notice here, as we begin to approach our way to to more localized behavior, we see a deviation at the largest row in the magenta color. Deviation of theory from experiment. So the theory predicts less intensity, but we have more intensity at these largest rows. And at the mobility edge and beyond, at the mobility edge is where we cross over into the localized regime, which has been done for this one sample in the middle here. We see a complete bend over and saturation of the width squareds in time. And not only that, but we still see this huge deviation at the largest row. And so up to this point, one might say that this extra signal at the largest row is due to these induced electric dipole-dipole interactions. And so to make a more educated, or to verify this assumption, one can make an experiment where we take the sample and we make it a conductor, or we coat it with a conductive material in order to inhibit these induced electric dipole-dipole interactions, which is exactly what we did. We took the coat, we took the mesoglass sample, and we silver coated it with a high conductivity, low viscosity material. This silver coating or silver paint is used in SEM, I think, microscopy. And so, yeah, the entire sample was coated. And when we took the coated and the uncoated sample and we measured the resonance frequencies, we see a shift to the left as a result of the coating. Unlike when you add beads to the system, you see a shift to the right. Here are the results for the transmission coefficient. So we see a lot more signal coming through at all frequencies, a few dips at 0.9. I think the dip has completely disappeared as a result of the coating. And again, as you add a coating, you increase the bond size between each bead, and so you lose scattering, or the spherical nature of each bead gets lost in a sense. And then the ballistic parameters, we get a KL that is larger than 1 here, indicating that we might not be able to achieve localization or to reach that regime, which is, again, is what we saw. So we see the diffuse regime, the subdiffuse regime, and the near localized regime, which is as far as we could get with the sample after coating it. And so, but the most important thing to note here is that in the magenta color at the largest row, these deviations are still there. They're persistent, and not only that, they don't seem to decrease. So they're still there, right? This anomalous extra signal is still there, even though we coated the entire sample with a conductive material. So in essence, since that is the case, we need to draw a different conclusion, or to get back to the board, the drawing board. Okay, and so to summarize here, we measured the resonant frequencies of one bead as well as multiples of beads in mini samples, and we saw the effect that silver coating has on one bead, which is a shift to the left as a result of coating. And then we saw, as we increased beads inside of the system, we saw a shift to the right in the resonant frequencies and a broadening in the same direction. We measured the coherent pulse, which gave us information about which gave us phase velocity and scattering mean-free path, which we were able to use to get information about the scattering of the sample. And then from studying the lateral expansion of the intensity in time and position, we're able to achieve or attain the mobility edge and localize it. So we have Anderson localization in a dielectric a mesoglass at small rho. But then we do see significant discrepancies between the data and the theory at the largest rhos. And then we try to tackle that using a silver coating. However, these anomalous contributions to the signal at the largest rho persist despite the coating, without a reduction in the deviations at the largest rho. And so in conclusion, we have evidence of Anderson localization of ultrasound in dielectric mesoglasses. Anomalous signal contribution is not due to the electric dipole-dipole mechanism, as described by Levitov. And then a potential mechanism responsible for this added signal includes, or could include, surface waves, which are only apparent at the largest rhos. And then some of the perspectives would be to conduct experiments on purely piezoelectric samples, which is expensive, but again, it's a perspective. This would amplify the induced electric dipole-dipole interactions to its maximum, and so that would help understand how much of this effect is actually appearing in the data, or to extend the SET theory to account for dipole-dipole interactions, because it does not so far have this, it doesn't account for it yet. So that would be another perspective. And so with this, I conclude my presentation. Thank you. I'm glad you enjoyed it, and I wish you all the best. Take care.